Power electronics is the application of solid-state electronics to the control and conversion of electric power. It also refers to a subject of research in electronic and electrical engineering which deals with the design, control, computation and integration of nonlinear, time-varying energy processing electronic systems with fast dynamics. The first high-power electronic devices were mercury arc valves. In modern systems, the conversion is performed with semiconductor switching devices such as diodes, thyristors and transistors, pioneered by R.D. Middlebrook and others beginning in the 1950s. In contrast to electronic systems concerned with transmission and processing of signals and data, in power electronics substantial amounts of electrical energy are processed. An AC-DC converter is the most typical power electronics device found in many consumer electronic devices, e.g., television sets, personal computers, battery chargers, etc. The power range is typically from tens of watts to several hundred watts. In industry, a common application is the variable speed drive that is used to control an induction motor. The power range of ESDs start from a few hundred watts and end at tens of megawatts. The power conversion systems can be classified according to the type of the input and output power: AC to DC, DC to AC, DC to DC, AC to AC. History. Power electronics started with the development of the Mercury arc rectifier. Invented by Peter Cooper Hewitt in 1902, it was used to convert alternating current into direct current. From the 1920s on, research continued on applying thyrotrons and grid-controlled mercury arc valves to power transmission. Uno Lamb developed a mercury valve with grading electrodes, making them suitable for high-voltage direct current power transmission. In 1933, selenium rectifiers were invented. In 1947, the bipolar point-contact transistor was invented by Walter H. Brattain and John Bardeen under the direction of William Shockley at Bell Labs. In 1948, Shockley's invention of the bipolar junction transistor improved the stability and performance of transistors, and reduced costs. By the 1950s, higher power semiconductor diodes became available and started replacing vacuum tubes. In 1956, the silicon-controlled rectifier was introduced by General Electric, greatly increasing the range of power electronics applications. By the 1960s, the improved switching speed of bipolar junction transistors had allowed for high-frequency DC-DC converters. In 1976, power MOSFETs became commercially available. In 1982, the insulated gate bipolar transistor was introduced. Devices. The capabilities and economy of power electronics system are determined by the active devices that are available. Their characteristics and limitations are a key element in the design of power electronics systems. Formerly, the mercury arc valve, the high vacuum and gas-filled diode thermionic rectifiers, and triggered devices such as the thyrotron and ignitron were widely used in power electronics. As the ratings of solid-state devices improved in both voltage and current handling capacity, vacuum devices have been nearly entirely replaced by solid-state devices. Power electronic devices may be used as switches, or as amplifiers. An ideal switch is either open or closed and so dissipates no power, it withstands an applied voltage and passes no current, or passes any amount of current with no voltage drop. Semiconductor devices used as switches can approximate this ideal property, and so most power electronic applications rely on switching devices on and off, which makes systems very efficient as very little power is wasted in the switch. By contrast, in the case of the amplifier, the current through the device varies continuously according to a controlled input. The voltage and current at the device terminals follow a load line, and the power dissipation inside the device is large compared with the power delivered to the load. Several attributes dictate how devices are used. Devices such as diodes conduct when a forward voltage is applied and have no external control of the start of conduction. Power devices such as silicon-controlled rectifiers and thyristors allow control of the start of conduction, but rely on periodic reversal of current flow to turn them off. Devices such as gate turn-off thyristors, BJT and MOSFET transistors provide full switching control and can be turned on or off without regard to the current flow through them. Transistor devices also allow proportional amplification, but this is rarely used for systems rated more than a few hundred watts. The control input characteristics of a device also greatly affect design. Sometimes the control input is at a very high voltage with respect to ground and must be driven by an isolated source. As efficiency is at a premium in a power electronic converter, the losses that a power electronic device generates should be as low as possible. Devices vary in switching speed. Some diodes and thyristors are suited for relatively slow speed and are useful for power frequency switching and control. Certain thyristors are useful at a few kilohertz. Devices such as MOSFETs and BJTs can switch at tens of kilohertz up to a few megahertz in power applications, but with decreasing power levels. Vacuum tube devices dominate high power at very high frequency applications. Faster switching devices minimize energy lost in the transitions from on to off and back, but may create problems with radiated electromagnetic interference. Gate drive circuits must be designed to supply sufficient drive current to achieve the full switching speed possible with a device. A device without sufficient drive to switch rapidly may be destroyed by excess heating. Practical devices have non-zero voltage drop and dissipate power when on, and take some time to pass through an active region until they reach the on or off state. These losses are a significant part of the total lost power in a converter. Power handling and dissipation of devices is also a critical factor in design. Power electronic devices may have to dissipate tens or hundreds of watts of waste heat, even switching as efficiently as possible between conducting and non-conducting states. In the switching mode, the power controlled is much larger than the power dissipated in the switch. The forward voltage drop in the conducting state translates into heat that must be dissipated. High-power semiconductors require specialized heat sinks or active cooling systems to manage their junction temperature. Exotic semiconductors such as silicon carbide have an advantage over straight silicon in this respect. And germanium, once the mainstay of solid-state electronics, is now little used due to its unfavorable high-temperature properties. Semiconductor devices exist with ratings up to a few kilovolts in a single device. Where very high voltage must be controlled, multiple devices must be used in series, with networks to equalize voltage across all devices. Again, switching speed is a critical factor since the slowest switching device will have to withstand a disproportionate share of the overall voltage. Mercury valves were once available with ratings to 100 kV in a single unit, simplifying their application in HVDC systems. The current rating of a semiconductor device is limited by the heat generated within the dies and the heat developed in the resistance of the interconnecting leads. Semiconductor devices must be designed so that current is evenly distributed within the device across its internal junctions. Once a hot spot develops, breakdown effects can rapidly destroy the device. Certain SCRs are available with current ratings to 3000 amperes in a single unit. Solid-state devices